All right, so this video is going to examine some gas laws that you most likely covered in your first year chemistry class. When we are looking at properties of a gas, we are able to keep in mind that gases are going to fill up any container that they have available. They are easily compressed. When they mix completely with other gases, and they are able to exert a pressure. And that's going to be based on their collisions, the force that they can apply per a given unit area on their surroundings. The four properties of a gas that we can examine quantitatively include its pressure, its temperature, the volume of your gas, and the amount of gas that is present. So, speaking of pressure, Torricelli was known for inventing the barometer, which is used to measure your atmospheric pressure. It uses mercury that will rise based on that atmospheric pressure. And when you are at sea level, if you're at standard pressure, 1 atmosphere, it will rise, 760 millimeters of mercury. The pressure that the atmosphere is applying on it pushes that liquid up into the barometric tube. Pressure can vary. It can vary depending on your altitude above sea level, as well as the environmental conditions that are taking place. So these are units of conversion between pressures. Again, standard pressure is defined as 1 atmosphere, and at that particular pressure at sea level, the barometer rises 760 millimeters of mercury. So that's that equivalency. Torricelli also got a unit named after him, and that is equivalent to the millimeters of mercury, 760 torr. And then we have the SI units of pressure, 101,325 pascals, or in kPa, 101.325. So this first problem is just to review with you how you would do a conversion between these types of pressure units. This is something you might need to do as part of another gas problem. It's not one that you would be asked to do separately. Here you have what pressure in torr is equal to this 57.9 kPa. So if that's what we have to begin with, and we know that 1 atmosphere is equal to 101.325 kPa, and that 1 atmosphere is equal to 760 torr, then when we set up our conversion, we can set those two quantities equal to one another. And when we go through and do the math, the 760 is a defined quantity. It will not affect your sig figs. So we're going to have 3 sig figs in our answer, 434 torr. So these laws that we're going to examine today are going to involve 2, 3, or all 4 variables that we can measure regarding gases. Boyle's is going to look at the relationship between pressure and volume, and that relationship, as you can see on the graph, is an inverse relationship. When one of the quantities increases, the other one will decrease. So if we're going to look at a gas at 2 points in time where the amount of the gas and the temperature of gas is being held constant, and let's say the volume of the container in which the gas is being held expands, the collisions are going to decrease, so the pressure will decrease. If the volume of the container that contains the gas is allowed to be compressed, then you will see as it gets smaller, your pressure will get larger. Units have to be consistent, but you can use whatever units you want for pressure or for volume to explore this relationship. So here we have 35 milliliters of a gas at standard pressure. Remember, standard pressure again is that 1 atmosphere. Pressure goes up to 2.5. What is the new volume? So if our pressure increased, our volume should decrease. So we have the pressure and volume of our gas at one point in time, 1 atmosphere and 35 milliliters. We know at the second point in time, our pressure went up to 2.5. And from those pieces of information, we should be able to solve for V2. And when we do our math through, we get that V2 is 14 milliliters. Our measurement with a few sig figs had 2 sig figs. So our volume did go down as our pressure went up. Charles' law and the rest of these 2 property gas laws are going to represent direct relationships. As one of the quantities increases, so will the other. Anytime you have temperature as a part of your gas law, since you can have negative Celsius temperatures, these laws were developed using the Kelvin form of temperature to account for that negative characteristic associated with Celsius. And by using Kelvin, you cannot have a negative temperature, which means you can't have a negative volume, a negative pressure, or a negative amount. And all those quantities are not plausible. So if they're both going to be increasing proportionally or both decreasing proportionally, we would have V1 over T1 equals V2 over T2. In a linear expression, when you cross multiply, V1 would go with T2 and V2 would go with T1. Your volume units, again, can be whatever you would like as long as they are consistent. Temperatures, however, must be in Kelvin. So here the volume of our gas doubled from 25 to 50 milliliters. If the original temperature was 25 degrees Celsius, what would be the new temperature in Celsius? So even though we're starting with the Celsius temperature and we want to end with the Celsius temperature, we still need to use Kelvin in our gas law. And if our volume is doubling, and this is a proportional relationship, we would expect our temperature to double. But remember, it's the Kelvin temperature that has the relationship with volume, not the Celsius temperature. So if we substitute in the variables that we know our initial volume was 25 milliliters. T2 is the new temperature, that's what we're wanting to find. We know that the second volume was 50 milliliters and that the original temperature was 25. Converted to Kelvin would be 298. Sorry, I should have put 298.0. It's not going to affect your sig figs, though, I promise. When you do your math through and you cancel out the 25 milliliters on both sides of the equation, we get that T2 was doubled from 298 Kelvin to 596 Kelvin. But remember that to go from Celsius to Kelvin, you add 273. To go backwards, you subtract it. And so our Celsius temperature was 323 degrees Celsius. Avogadro's law explores the relationship between volume and amount. As your amount of gas increases at a constant pressure and a constant temperature, the volume of the container containing the gas would have to increase as well to balance out that pressure shift. So V1 would go with N2 and V2 would go with N1 in the direct relationship if I was going to set it as an equivalence statement. Volume and quantity need to be consistent unit-wise. You could have your quantity be in moles or you could have it be in grams. Because it's the same gas, it would be changed by the same proportion to moles. So here we have 0.1 moles of oxygen gas. It occupies 15 milliliters at 0 degrees Celsius. What would the volume be of 0.3 moles of oxygen gas if it's at the same temperature and pressure? So the temperature and pressure aren't changing. We only are exploring the relationship between volume and moles. V1N2 equals V2N1. Our moles tripled, so we would expect our volume to triple. We know what our initial volume was. We know it was initially 15 milliliters, and we know what the amount was at the second point in time, 0.3 moles. We want to find what the new volume would be, and we have our initial amount, 0.1 moles. So if we go through and do our math, and we account for sig figs, we get that the volume did indeed triple to 45 milliliters. This is going to be the last of our two variable gas laws. Gay-Lussac accounts for the relationship between pressure and temperature. As the temperature of a gas increases, if the volume is staying constant and the amount is staying constant, the pressure will have to increase to account for that increase in kinetic energy. So P1 goes with T2 and P2 goes with T1 in the linear relationship. But with any direct relationship, it is proportional in terms of fractions. P1 over T1 equals P2 over T2. Pressure units can be whatever you would like, but temperatures have to be in Kelvin. So here we have a fixed amount of gas, has a pressure of 76.2 kPa at negative 10 degrees. What will its pressure be at negative 45 degrees Celsius? So our temperature is decreasing, so our pressure should decrease as well to account for that change in temperature. So again, looking at our linear relationship, we want to find P2 P1 would be the initial pressure, 76.2 kPa. T2 would be that negative 45 degrees Celsius converted to Kelvin by adding 273, 228 Kelvin. P2 is what we're looking for, and T1 would be our initial temperature converted to Kelvin, 263. We do our math through and we account for Kelvin. All of our measurements had 3 sig figs, so we would want to have 3 sig figs, and our pressure did indeed drop to 66.1 kPa. At this point, when we start to get into more than 2 variables at a time, we cannot hypothesize what the change will be proportionally, because you no longer have just one quantity being changed and examining that effect on another. With combined gas law, we have a constant amount of gas, and we are manipulating its pressure, its volume, and its temperature. Just like with the Boyle's and the Charles and the Gay-Lussac laws, pressure and volume can be in whatever units you would like, but temperatures have to be in Kelvin. You are welcome to use the fraction. If you prefer the linear equation, you can use that one as well. So here we have 45 mils of an ideal gas. It's initially at 15 degrees Celsius and 740 millimeters of mercury. The volume got doubled and its temperature was reduced by a third. We want to know what its new pressure will be. So we want to find P2, which means we want to solve for this relationship in terms of P2. So we would want to plug in what we know. P1 is our 740 millimeters of mercury. B1 is our 45 milliliters, but we want to use the second temperature. You were told the temperature got reduced by 1/3. The initial temperature was 15 degrees Celsius, so if it got reduced by 1/3, it would go down to 10, and that converted to Kelvin would be 283. P2 is what we're trying to find. V2 is the volume that got doubled, so 45 doubled will become 90. And T1 was our initial temperature. When we convert that to Kelvin, we get 288. So we isolate P2, take care of our units, multiply and divide. The measurement with the fewest sig figs is 2. So our final pressure, our new pressure, will be 360 millimeters of mercury. The last gas law that we're going to review right now is the ideal gas law. And you will notice that this one's kind of different from all the other ones that we've talked about today, because there's no ones and twos. PV, PV equals nRT. R is a gas constant, and it is being used to account for that second point in time. That R is calculated for a mole of gas at STP. We know that at STP, you are at a temperature of 0 degrees Celsius, a pressure equivalent to 1 atmosphere, and if you have 1 mole of a gas, it occupies 22.4 liters of space. So by substituting all of those quantities into the ideal gas law at a second point in time, we get a constant that we can use to examine another point, and not have to substitute in 8 different quantities into a single gas law. The ideal gas law exists for gases that typically are thought or hypothetically thought to behave ideally. What that means is that they are going to follow the tenets of the kinetic molecular theory, that they don't attract to each other, they don't repel one another, they take up whatever space is available, they're in constant random motion. Real gases don't always obey those characteristics of the kinetic molecular theory. The kinetic molecular theory is applicable to gases at lower pressures and higher temperatures. When you start to get your pressure to be elevated, or you start to have your temperature drop, the real gases will start to stick more to one another than they would if they were truly behaving ideally. That's going to reduce their volume, and that's also going to cause changes in their pressure, and those have to be accounted for when you're not under ideal conditions. So the gases that we are working with are hypothetical. but we are going to assume that they are behaving ideally as long as they are below that pressure of 1 atmosphere. So here we have 2 moles of helium gas. It's at a volume of 34.5 liters, and it's at a temperature of 22.5 degrees Celsius. We want to find the pressure in atmospheres. So if we take that ideal gas law, PV equals nRT, and we isolate P, we get that nRT gets divided by V to find that value for P. Now, because the constant has set units, that determines what units we need to have our N, our T, and our Vn. Our N is our moles, 2.00, and that works out with your constant, which is divided by moles. Our temperatures, no matter which gas law we're working with, have to be in Kelvin. So after we add 273 to 22.5, you get 295.5, and that again works out with your constant R. And your volume and your constant is in liters, so we need to divide all 3 of those quantities by 34.5 liters. The moles, the liters, and the kelvins go away, and when we do our math through and account for sig figs, we get a pressure in atmospheres because that constant was in atmospheres, and that's what we wanted to find. If we had wanted to have a pressure in another unit, we would have had to do a conversion to get there. So this ideal gas law problem is going to involve several conversions. We have an argon gas that's at a volume of 750 milliliters. It's initially at a temperature of negative 5.3 degrees Celsius and a pressure of 90.5 kPa, and we want to find its mass. Well, in our ideal gas law, there's only one quantity that has anything to do with amount, and that would be N. So if we solve for N, we would get PV divided by RT. Remember, with your constant, you need to have your pressures in atmospheres. So we would need to convert that 90.5 kPa into atmospheres. We would need to convert our volume that's in milliliters to liters, so that'll work out with our constant. And we need to change our temperature to Kelvin. So if we do those different conversions using the relationship that 101.325 kPa is equivalent to 1 atmosphere, we get our atmospheric equivalent to 90.5 kPa to be 0.893 atmospheres. Our volume would need to be divided by 1,000 to account for the relationship between milliliters and liters, 0.75 liters. And when we convert our temperature in Celsius to Kelvin by adding 273, we get 267.7 Kelvin. The atmospheres, the liters, and the kelvins cancel, and you end up, when you account for sig figs, with 0.030 moles. But we were asked to find the mass of our argon gas, and we can relate moles to mass using the molar mass of argon, 39.95. So once we have done that final conversion, we get what the actual mass was of our argon gas, 1.2 grams.